Okay, so what we're going to cover in this section is we're going to expand on what we did in section 1. So literally our goal here is going to be to solve a system of linear equations with 3 equations and 3 variables. So keep in mind that when I say this, we could have system of equations larger than 3. And so the process that we use to solve the 3 variables and 3 equations will be identical to any other case, where if we have 4 equations, 4 variables, and so on. So for instance, our goal is going to be to deal with systems that look like this. 2x minus y minus 3z equals to negative 10, and x minus y plus 2z equals to 1. So this is an example of what we're going to be doing. So our goal is to solve for this. Now you could see that as far as the method we'll use to solve this, it will not be the same as last section, because now we have 3 variables. So can we use substitution? Possibly, but it'll just become more complicated there. So we'll have to kind of I'll show you the method we'll use, and that's a pretty common method used by everyone. So we'll get into how to solve a system like this momentarily. So one thing I want to do is I just kind of want to describe what these guys look like visually, because people usually think that, hey, since we're calling it linear equations, and when we're adding the z dimension, where we're making this 3-dimensional, people think this is a 3-dimensional line, and not quite. So we know that linear equations of the form ax plus by plus cz equals to d are visually represented as planes. So now what we're doing is we're actually solving the solution for planes. So if I have these 3 planes, when I'm trying to find the solution, I'm trying to find the solution of where these 3 planes intersect. So before we go any further, what I want to do is, just like in section 1, I want to first talk about, hey, what are the possible solutions of these types of systems? So of these systems are, and so the first possibility is, well, exactly one solution. So what does that mean? The planes all meet at just one point. Okay. Now the second possibility is they have infinitely many solutions. So that means that the planes meet at infinitely many points. But in a minute I'll show you visuals of this. The book actually has a really nice visual of it, so I'm just going to use the book's visual in a minute, and then we'll see exactly how that looks. And the last possibility is no solution, which would mean that the planes do not intersect, or the 3 planes never all intersect at any point. So visually speaking, here's what we're kind of looking at. So if I bring the book over, see, here's kind of what we have. So what is it that we notice here? We have 3 planes. There's the red plane, the blue plane, and the yellow plane, and these 3 intersect at just that one point right there. So we could see that this has only one solution. Now, where's the case for infinitely many solutions? Look at these 3 planes, right? So we have these 3 planes where they all meet at that same line. Now remember, planes extend outwards forever. So even though we draw it and it looks like it ends, planes are never ending. So technically speaking, these three planes, they intersect at every point that lies on this line if I draw it out up and down forever. Okay, now the last possibility is this picture right here. So what do I notice here? Here's an example where we have three planes, but notice how two of the three planes intersect one another in this picture. But what do you notice? All three planes never intersect at exactly one point or a line or whatever it may be. And remember, anytime we're trying to find a solution of a system of three variables and three equations, I need to find the point or the points, if any, in which the three planes all intersect one another. And so notice how this last one, they never intersect. This middle one, they intersect at infinitely many points, particularly speaking this line. And then these three planes only intersect at that point. Okay, so those are the three possibilities. So once again, when we solve these systems, we'll know as we get closer to the solution, it'll become more apparent as to which one of these, which solution we have. Okay, so going back to our notes. Before we actually start solving systems, let's talk about kind of things we are allowed to perform on the system of equations. So when we're solving systems of linear equations, with three variables. So that's kind of where we're headed now. So we would now say, well, when solving a system of equations, we can perform the following operations. So this is going to be important because what I'm going to show you, or what we're going to talk about now, is there are certain things we can do through our system of equations. And these three operations that I give you right now, what it will do is it will still leave the solution, or it'll make the solution consistent with the original system. So these are operations that we can perform on the system of equations that will not change the result of the system of equations. So one possible operation we can perform is what? We can add a non-zero multiple of one equation to another. So what this is saying is we can grab any row of our system of equation and we could multiply it by some constant, as long as it's not zero, because we don't want to zero anything out, and I could add it to another row, and that's fine. Nothing will happen to our system. Okay, so and that's because we're literally, all we're doing is we're just combining what we have to begin with, so we're not really changing things up, right? We're just kind of making them look different, but it's just a multiple of one row to the other, which is leaving things, as far as our solution goes, it's not changing our solution. Okay, so then we can grab any equation. So I can grab any equation, I could multiply that equation by a non-zero constant. Okay, so what I could do is I could say, for example, I want to grab the second equation, I want to multiply that by 3, and that's fine. There's nothing wrong with that, and that will still leave my system, as far as the solutions go, unchanged, right? I'm not really changing the system up. And then the last thing we could do is we can interchange any two equations. So in other words, we can swap any two equations, right? So coming back to this equation, if I were to grab the first row and the second row, and if I were to swap them, it wouldn't change the system, right? It may look different, but it would still leave it the same. So these are the three operations that we're going to stick with, okay? So now, if we generalize this now and try to see, well, how would I go ahead and, or what's the approach that we're going to take with this? Let me go to the back page so we have plenty of room. And let's talk about how we would solve these systems. And then we'll do a bunch of examples, and then that'll basically wrap things up for us. So for the system, if I give you a system of this form, and I'm just going to generalize it, so ax plus by plus cz equals to d, ex plus fy plus gz equals to h, ix plus jy plus kz equals to L, and obviously the letters A through L, we're just treating those as any constant, right? So our goal to solve this system, and here's how we're going to see exactly what the approach we should take. So the goal here is to use row operations to turn. And what we're going to do is, before I get into that, is if I take the lower three entries below the main diagonal, which is this, right, this lower triangle, right? We could have also done the same thing to the top, but let's just stick to the bottom. So our goal is to grab these three entries, and we want to use row operations and to turn these three entries into 0. So we want to turn these into zeros. Okay, so we'll in a minute I'll explain to you why that helps us once we turn these into zeros, why that'll allow us to get into the solution. Okay, but by doing this, what we're doing here, so this is called triangular form. So what I've done is you basically put this in triangular form, meaning that I turned the bottom three terms into zeros, or you could have also done the upper three terms above the main diagonal into zeros. Then what's going to happen is, so here's how we'd solve for this. Once you turn these into zeros, then what do you notice? See, if these two are zeros, then what could you solve for? You could solve for z. And if you solve for z, then you could come up here and replace z here with what you solve for down there. And then what do you notice? This is a 0, which will allow you to solve for y. And then once you know what y is, then you could come up here, substitute for z, substitute for y, and then you could solve for x. So we could see the key is here. Once we turn those into zeros, everything else kind of opens up because we're using substitution. So then once we use the process of substitution, so then we're going to say then we're going to use the process of substitution of then substituting to solve, which is what we're going to be doing. That's known as Gaussian elimination. So is called Gaussian elimination. So just keep in mind that when we say, hey, solve this using Gaussian elimination, all we want to do is turn these guys into zeros, and then we want to substitute, solve for z, substitute, and then solve for y, and then substitute up here and solve for x. Now, one comment I want to make is this. Whenever you're trying to turn these three into zeros, what we want to do is we want to turn these two entries into zeros first. So we would say turn these into zeros first. Now it doesn't matter which one you turn into a zero, but just make sure these two are turned into zeros first. Then you turn that into a zero last. So we're going to say turn this into a zero last. Okay, so with that said, what we could do now is we can do some examples where we'll use row operations to turn these guys into zeros. So for example 1, we're going to say that we're solve the system using Gaussian elimination. So now that we have this right here, we can say my system is x minus 2y plus 3z equals to 1, x plus 2y minus z equals to 13, and lastly we have 2x plus 4y minus 7z is equal to 11. So now what we're trying to do here is we are trying to solve for practically this system. Now if you remember, what we said earlier was that our goal is to turn these guys into zeros using row operations. So I'm going to start off by turning this into a zero. Now the notation I use, so let's just make sure that we understand. What am I going to do? See, to turn this into a zero, I can use row. In fact, I want to use this guy. How come? Because this is just 1x. And since this is 1x and this is also 1x, I can make this the opposite of that. So when I add it to this, it'll easily zero out. So what I'm going to do is I'm going to say, well, my notation that I'm going to use, and hopefully you guys can follow along with this, I'm going to say negative row 1 plus row 2. And usually the way I like to use my notation is what? The row I write second, so this is the row that is being changed, right? And then the row that I write first, so the first row isn't going to change, but I'm using, so we are using this row to change the next row, right? To change, so in other words, I'm using this row to help me change that row. So when I'm saying negative row 1 plus row 2 in this notation, all this notation is saying what? Grab row 1, multiply it by negative 1, and add it to row 2. And when you do that, you're changing row 2, row 1 stays unchanged. So the way this system is going to look now is what? Remember, row 1 is not changing, so it'll still just be x minus 2y plus 3z equals to 1. Now what am I doing? I'm changing row 2. And how's row 2 going to change? I'm going to grab row 1, multiply it by a negative, and then add it to row 2. So look, negative times 1x is negative 1x plus 1x, that's 0. And see, and that's how we're getting our zeros. And hopefully you see why I needed a negative here, because I wanted these guys to be opposite, so when I add them this would zero out. Okay, so then negative times negative 2y becomes 2y, and then what am I going to do? Add it to row 2, which 2y plus 2y, that becomes 4y, and then negative 3z, right? If I add this, multiply this negative to the 3z, it becomes negative 3z plus negative z, that becomes negative 4z, and lastly negative 1 plus 13 becomes 12. And then now what do I have? 2x plus 4y minus 7z equals to 11. Okay, so remember what I said earlier. So we got 1 0. Now we need to turn these two into zeros. Now if you remember earlier on, I said what's our goal? To turn these two into zeros first. So that's become a 0. Now I need to turn this into a 0. Now what do you notice? The only row I could use to turn this into a 0, it has to be the first row. It can't be the second row, because no matter what I multiply to this 0, it's not going to become negative 2. And more importantly, what I notice is since this is a 1, I could easily turn this to the opposite of that. See, what number would I need to multiply to this to make it the opposite of 2x, which I'm sure by now you've guessed, I would have to multiply negative 2. So to turn this into a 0, I need to grab row 1, so my notation is going to be what? Negative 2 times row 1, right? So what am I doing? This is saying I'm going to grab row 1, multiply it by negative 2, and I'm going to combine that to row 3. So this notation is saying, once again, I'm changing row 3. So row 1 is not changing, so this will just be x minus 2y plus 3z equals to 1. And I hope this makes sense to you. If not, ask me to clarify and I'll go into greater detail next time we have a conversation about this. But now what's going to happen is the second row also isn't being changed, but the third row is going to be changed. And what is the third row going to turn into? This is saying the third row is going to become what? My new third row is going to become when I combine negative 2 times row 1 to row 3. So negative 2 times x is negative 2x plus 2x. That's a 0. And then negative 2 times negative 2y, that becomes 4y plus 4y is 8y. and then negative 2 times 3z is negative 6z plus negative 7z, that's minus 13z, and finally negative 2 times 1 is negative 2 plus 11 is 9. Okay, so we're almost done before we start substituting. The next step is going to be what? We want to pretty much grab this now, turn that 8y into a 0. And here's where we have to be careful. I don't want to use row 1 to turn this 8y into a 0. Now let me explain to you why. You might look at row 1 and say, yeah, why not? I could just grab this row and multiply it by 4, because if I multiply the negative 2y by 4, I'll get negative 8y, and when I add it to 8y, that'll zero out. But here's what we've overlooked. If I use row 1, what do you notice about this entry? That's non-zero. And so when I multiply this row, let's say by 4, and I add it to this 0, that'll become non-zero again. So how do I make sure that this stays 0? Well, guess what? Use row 2, okay? Because row 2, what do we notice that we like? This first entry is a 0, and I like that because no matter what I multiply to this, it's going to be 0, and when I add it to 0, it'll stay 0. So remember, when we turn these guys into zeros, I don't want this to become non-zeros ever again. So what you notice is to turn this 8y into a 0, I'm forced to use the second row. So since this is 4y, what would I have to multiply to this row to make it the opposite of 8y? And I'm sure you've guessed, we'd have to multiply by negative 2. So this would be what? Negative 2 times row 2 plus row 3. And when I do that, once again, so this is saying we're going to change row 3. So row 1 and 2 are staying unchanged. So x minus 2y plus 3z equals to 1. And then we have 0 plus 4y minus 4z equals to 12. Now, here's where we have to take negative 2 times row 2. Now look at how nice this is. See, negative 2 times 0 is 0, plus 0 stays 0, which notice how we kept that as a 0, which that's crucial. We want that to be the case. So then negative 2 times 4y is negative 8y plus 8y. That's another 0. And then negative 2 times negative 4z, that's 8z minus 13. That becomes minus 5z equals to negative 2 times 12 is negative 24 plus 9. That negative 24 plus 9 is going to be negative 15. Okay, now what do you notice? We got the 3 zeros that we desired. Now we could easily solve for this to finish our Gaussian elimination. So what do we know? If I start with the last row, we know that negative 5z equals to negative 15, which implies if I divide both sides by negative 5, z is 3. And then what do? We can now come up to the next row, the one above it. Now that we know what z is, I could substitute 3 for z and I could solve for y. So what do we have now? So if I take the second row, it'll be 4y minus 4 times 3 equals to 12. And what is it that we notice? 4y minus 4 times 3. So that becomes what? 4y minus 12 equals to 12. And then if I add 12, I get 4y equals to 24, which then if I divide both sides by 4, I get y is 6. Okay? And then lastly, to find x, then I come up to the top equation, I substitute 6 for y, 3 for z, and I solve. So this becomes x minus 2 times y is 6 plus 3 times z is 3 equals to 1. Right? So hopefully you see what I'm doing here. I'm just plugging in what I have for y and z here. That will allow me to solve for x. So what does this become? X minus 12 plus 9 equals to 1, which implies x minus 3 equals to 1, and that gives me that x is equal to 4. So what we notice is there's only one solution. And what is the solution? These three planes intersect at the point 4, 6, 3, right? Because that's x, y, and z, and that's our answer. Okay? So let's move on to our second example, which example 2 says solve the system x plus 7y minus 7z equals to 3, 3x plus 14y minus 16z equals to 17, and 2x plus 7y minus 9z equals to 10. So now, once again, what am I going to do? Let's start off by turning this into 0. So what do I notice? The easiest row to work with is probably row 1. I could use row 3 to also turn this into a 0, but whenever we have a 1, it's always easier to go after that. So if I grab row 1, I'm going to grab row 1 and multiply it by negative 3 times row 1, and I'm going to add that to row 2. So what's going to happen here? This will be 1x plus 7y minus 7z equals to 3. Now remember, I'm changing row 2, right, because of my notation. So negative 3 times 1x is negative 3x plus 3x, that's 0. Negative 3 times 7y is negative 21y plus 14y is negative 7y. Okay, and then negative 3 times negative 7z, that's 21z, minus 16z, that becomes 5z. Negative 3 times 3 is negative 9 plus 17, that's 8. Okay, and then we have 2x plus 7y minus 9z equals to 10. Okay, now what do we want to do now? We want to turn row 3 into a 0, and once again I have to use row 1. So what do I do to turn row 3 into 0? I'll grab row 1 and I'll multiply it by negative 2 times row 1, and I'll add it to row 3. And if I do that, what do I have here? I get x plus 7y minus 7z equals to 3. 0 minus 7y plus 5z equals to 8. And now what do we notice? Negative 2 times x is negative 2x plus 2x is 0. Negative 2 times 7 is negative 14y plus 7y is minus 7y. Negative 2 times negative 7 is going to be 14z plus 9, that's 5z. And then negative 2 times 3 is 6 plus 10, or negative 6 plus 10 is 4. Okay, now what do we notice here? Well, what do I have? I have, now to turn this into a 0, I'm going to use row 2, which, what do I notice about this? This is negative 7y, that's negative 7y, so they're exactly the same. So I need to make this the opposite of that, which means just grab row 2 and multiply it by a negative and then add it to row 3. And if I do that, what happens here? We get x plus 7y minus 7z equals to 3. And then remember, row 2 is not changing, I'm changing row 3, so row 2 will remain the same as this. And then now what will happen? Negative times 0 is 0 plus 0, that stays 0. Negative times negative 7y is 7y plus negative 7y, that becomes 0. Negative 5z plus 5z, that becomes 0. Now we're noticing something here. See, going through this process, we're getting a bunch of zeros, which, what is this suggesting? Either I'm going to have infinitely many solutions or no solutions. So let's see, this last number will tell us. So negative 8 plus 4 is what? Negative 4. And what is it that we notice here? This last row is giving me something that makes no sense, right? 0 does not equal to negative 4. So why am I getting 0 equals to negative 4? Because when I'm trying to solve this system has no solution. So this basically means we have no solution. That means these three planes will never intersect anywhere at the same time, or all three won't intersect each other. So I'd like to point out, just like I did in section 1, see, how do we know that this had no solution or it has infinitely many or 1? We really don't. But going through the process of trying to turn these guys into zeros ourselves, if it has no solution, it'll make itself, we'll know before actually we get to a solution, right? So just keep that in mind. Are you expected to know if something will have no solution, infinitely many solutions, or one solution? Of course not. But you'll still follow the same process, and then at the end, you'll discover which one of the three cases it is, okay? So there's one more example I want to do, which would be for the infinitely many cases, and then that's where we'll stop. Okay, so for our third example, we're going to say solve the system x minus y plus 5z equals to negative 2, 3x plus y plus 3z equals to 2, and 3x plus 9y minus 21z equals to 18. Okay, so going through the same process again, to turn this into a 0, And by the way, just to kind of prove my point, I guess what we'll do is we'll do this. So let's turn this into a 0. Remember we said it doesn't matter which one we do first. So since these two are the same numbers, what could I do? I could say, well, why don't I just grab the second row, multiply it by a negative, and add it to the third row. And that'll basically make these opposites, which will help me zero this out. So I'm just doing this slightly differently just so you guys see that it doesn't matter what order we turn these into zeros. It's just that should be turned into a 0 last. So if I do that, what do I get? I get x minus y plus 5z equals to negative 2. Then we have 3x plus y plus 3z equals to 2. And lastly, this is saying we're changing row 3. So negative times row 2 plus row 3, that will be negative 3x plus 3x, that's 0. And then this will be what? Negative y plus 9y, that's plus 8y. And then we have negative 3z plus negative 21z, that's negative 24z. And then lastly, negative 2 plus 18 is 16. Okay? Now, to turn this into a 0, what am I going to do? Now, I have to use row 1 because obviously that 0 will I'll never be able to use the 0 to get a negative 3 out of. So I'm going to grab the first row and multiply it by a negative 3. So negative 3 row 1 plus row 2. What will that give me? I'll get x minus y plus 5z equals to negative 2. And then what will this be? Negative 3 times x is negative 3x. And by the way, this is not a negative, right? This is just positive 3x. So negative 3x plus 3x is 0. And then negative 3 times negative y is negative 3y plus y is negative 3y plus y is negative 2y, okay? Or sorry, no, that was correct. Negative 3 times negative 2 is positive 3y plus y, that becomes, so this is a 4y. Let's make sure we don't make a mistake because one small mistake will throw the whole thing off, right? So that becomes a positive 4y. And then negative 3 times 5z is negative 15z plus 3z is negative 12z. And then negative 3 times negative 2 is 6, plus 2 is 8. And then we have 0 plus 8y minus 24z equals to 16. Now to turn this into a 0, what do I have? I have a 4y here. Remember, we have to use the second row. I'll grab the 4y and I'll multiply it by negative 2. So this would be what? Negative 2 times row 2 plus row 3. And then I think we get the infinitely many solutions case, which I'll have to show you how to write this out because remember, when we say infinitely many solutions, we have to be more specific about it. So what do I notice? Negative 2 times 0 is 0. Oh, let me actually write out the second row. Plus 4y minus 12z equals to 8. So negative 2 times 0 is 0 plus 0 is 0. Negative 2 times 4y is negative 8y plus 8y is 0. Negative 2 times negative 12z is 24z plus negative 24z is 0. Negative 2 times 8 is negative 16 plus 16 is 0. Now notice what happens. When you get a row that completely zeroes out, what does that mean? Now we have infinitely many solutions. But what happens is we need to now be specific as to what we mean by infinitely many solutions. So when this happens, what do we notice? We have 3 variables, 2 equations, which means we need to free up a variable. And what do I mean by free up a variable? We just say, okay, look, from these 3 variables, this one could be any real number. And when you say this is any real number, that's how you're generating your infinitely many solutions. So I always like to go backwards. So I always make z my free variable, or I make z the variable that could take on any real value. And then what is it that we're going to notice? Y and x are all going to depend on z. So here's what we're going to do. Since a row zeroes out, I'm going to say let z be any real number. Okay, so then if z is any real number, then what is it that we know? We could write y in terms of z. So then we would say that 4y minus 12z is equal to 8, which implies 4y is equal to 12z plus 8, which if I then divide by 4, I get y is equal to 3z plus 2. So notice how, what is y saying? You tell me what z is and I could tell you what I am. right? And then how about x? Well, we do the same thing for x. And what is it that we have? X minus y plus 5z equals to negative 2, which what does that become? X equals to what? Y minus 5z minus 2, except I don't like this. So what have I done so far? I've solved for x, haven't I? And I don't like this. How come? Because x has to be strictly in terms of z. But then you say, but wait a minute. I know that y is 3z plus 2, so I could replace that y with 3z plus 2. So that becomes, this implies x is 3z plus 2 minus 5z minus 2. So all I did was I replaced y with 3z plus 2. Now what we notice is I could write x strictly in terms of z. So what does that imply? X equals to 3z minus 5z, that's negative 2z, and then 2 minus 2, that goes away. So what is it that we notice here? Z is any real number, and then whatever z is, then y is just 3z plus 2, and x is negative 2z. And why do I have infinitely many solutions? Because of the fact that z can be any real number. So my solution is going to be what? X, y, and z, right? So x is negative 2z, y is 3z plus 2, and lastly, z is just z, right? Because we're making z any real number. So what do we mean that there's infinitely many solutions? For example, if z is 0, a point that's a solution would be what? 0. So x would be 0. If z is 0, x would be 0, y would be 2, and z would be 0, obviously. So we could see that if z is 1, so z would be 1. What would y be? Y would be 3 times 1, which is 3 plus 2. Y would be 5. And what would x be? X would be negative 2 because z is 1, right? So when we say infinitely many solutions, we're not saying any point will work. We're just saying there are infinitely many points, which is here, that will satisfy this condition, okay? So just keep that in mind. If a row completely zeroes out, that means we're going to have infinitely many solutions, which means you're going to have to free up a variable. Now remember, it doesn't have to be z. It could be anything, right? So I always just go with z and work backwards because to me that's easier. But you could have made y a free variable or x and so on, okay? So just keep that in mind. But this pretty much wraps up this section. We're pretty much, hopefully you got the hang of how to solve these. And the process of how you know how many solutions there are, you don't know until you get to the final step, right? So just make sure if you have any questions, don't hesitate to reach out and ask your questions, and I'll be more than happy to help. But this pretty much takes care of this section.